Hello everyone and welcome back to another video. Today we're going to be returning to the Kalda mechanics series and we're looking at problems 14, 15, and 16. And of course we're still in the static section. So let's just get right into them. A light rod with length L is hinged in such a way that the hinge folds in one plane only. The hinge is spun with the angular speed omega around the vertical axis. A small ball is fixed to the other end of the rod. A. Find the angular speeds for which the vertical orientation is stable. B. The ball is now attached to another hinge and in turn to another identical rod. See the figure below. The upper hinge is spun in the same way. What is now the condition of stability for the vertical orientation? Alright, so let's start off with part A. And let's let these balls have mass m. And let's let it be displaced a small angle theta. And let's work in the rotating frame. And the reason we work in the rotating frame is because that turns it into a statics problem, which makes it easier. Because it's going to be difficult to analyze stability when you have when things are moving, right? So we have two forces here in the rotating frame. We have mg and we have m omega squared r, where r is the distance from the axis, and in this case it's the lowest order. Since it's L sine theta, it's approximately L theta. So to make sure this is stable, we can find the torque here and make sure that the net torque is taking it back. And that requires that the torque from this one has a greater magnitude than the torque from this one. So the moment arm for the gravitational force is to lowest order L theta. So we have mg L theta is greater than, and the moment arm here to lowest order is just L, so it's greater than m omega squared L squared theta. So we can cancel theta theta squared L m m, and that gives us omega squared is less than g over L. So that's part A, pretty simple. Or pretty simple once you get the idea. And now let's do part B. So part B is a little bit more tricky. Since we have 2 degrees of freedom here, it's going to be hard to analyze forces. So the way we deal with this problem is we use energy, and I believe I discussed this in a previous video. But if we plot potential energy versus x, then let's say it's like something like this. Then these local minima, these local extrema are the points of equilibrium, because F is equal to negative dv dx. So then that means the net force is 0. And if it's a local minima, then it means it's a stable equilibrium, because things will try to achieve lower energy. But you can also look at this as being always restoring. So, and we can also extend this to multiple x's. Then it has to be in some like 3D sort of figure. I don't know if this shape is too clear for you. It has to be some sort of local minima on the 3D graph. So that's what we're going to do here. Let's draw the diagram first. So we have 2 masses like this. I'm going to exaggerate the angle so that's a bit more clear. So let the angle be phi sub 1. And let's let this angle be phi sub 2. And we're working in the rotating frame again. So we want to find an expression for the potential energy. However, the potential energy is not simply the gravitational potential energy here, because we have a force, the centrifugal force, doing work. So we include that. And that means let's just do the gravitational one first, since that's really simple. It's for this mass here, it's going to be mgl times 1 minus cosine phi sub 1. And if we assume phi sub 1 is small, we can use the small angle approximation, and this reduces to phi sub 1 squared over 2. And then similarly for the second mass, it's mg times 2 minus cosine phi sub mgl times 2 minus cosine phi sub 1 minus cosine phi sub 2. And this approximates to phi sub 1 squared over 2 plus phi sub 2 squared over 2. And now we have to do the potential energy due to the centrifugal force. So we have the net work done is equal to, in general, if it's at a radius r, since the force is m omega squared r, if we integrate that over r, then we get m omega squared r squared over 2. So, and the potential energy is going to be negative because it means, because that's how it's defined. In other words, things try to achieve lower potential. So, m omega squared over 2, and then we can write r squared for each of these. For the first one, it's the lowest order, it's L phi sub 1, so it's L squared phi sub 1 squared. And for the second one, it's L phi sub 1 plus L phi sub 2 squared, which we can expand as L phi sub 1 L squared times phi sub 1 squared plus 2 phi sub 1 phi sub 2 plus phi sub 2 squared. And so we can write out the potential energy as mgl phi sub 1 squared, because there's a over 2 here and over 2 here, and then from here we have 2 phi sub 1, so again, so this time minus m omega squared L squared phi sub 1 squared. And now for phi sub 1 phi sub 2, we have a minus m omega squared L squared phi sub 1 phi sub 2. And with phi sub 2, we have phi sub 2 here and phi sub 2 here, and these are both over 2. So plus mgl over 2 phi sub 2 squared minus m omega squared over 2 phi sub 2 squared. So we have this expression here, and we need to find the omega such that it's this local minima in all, both variables. And we use the second derivative test, which for multivariables is, so let v sub 1 phi sub 1 be the partial derivative of v2 times v phi sub 2 phi sub 2, the same thing for phi sub 2, and then phi sub 1 phi sub 2 equals v phi sub 2 phi sub 1, the other remaining partial derivatives. So the second derivative test tells us that this squared minus these two multiplied has to be greater than 0 for it to be a local minimum. So this value here is equal to, all of this stuff is going to disappear once you take one of them and then take the other, but this is going to remain, so this is going to be minus m omega squared L squared, and these are partial derivatives just in case you didn't know. And phi sub 1, this is going to be 2 mgl minus 2 m omega squared L squared, and this is going to be mgl minus m omega squared L squared. So now from here we can set the determinant here equal to greater than 0. So m omega squared L squared is greater than 2 times mgl minus m omega squared L squared squared. And from here it's really just algebra. So m omega squared L squared is greater than root 2 mgl minus root 2 m omega squared L squared. Let's get rid of some L's and M's, and we get omega squared times 1 plus root 2 L is greater than root 2 G. And so this implies that, sorry, this should be flipped here because what I said earlier is not correct. The second derivative test tells us that if we multiply these two and subtract this squared, then it should be greater than 0. So yeah, so it should be a less than sign here, and this gives us that omega squared is less than, if we rationalize the denominator there, that will be root 2 times root 2, 2 minus root 2 over 2 minus 1, 1 times g over L. And so that's the answers to that part there. So it's a bit of a mathy problem at the end there. Not much actual physics, just kind of grinding through the equations there. But it's still worthwhile knowing how to do that kind of stuff. So let's move on to the next question, which is also a little bit mathy, I guess, more geometry. Before you start the next problem, I want you guys to be aware because my explanations were a bit confusing for this one, so feel free to ask any questions in the comments. And yeah, let me read it. If a beam with square cross-section and very low density is placed in water, it will turn one pair of its long opposite faces horizontal. This orientation, however, becomes unstable as we increase its density. Find the critical density when this transition occurs. The density of water is rho W equals 1000 kilogram per meter cubed. So I already have a diagram prepared here. The square cross-section is rotated, and let me draw the original water line here. So this is the original center of this water section, and once we rotate it, it should go to somewhere like here. And the original water line is that there. But it can be pretty clear that we can actually approximate this as going through this point here, which is the center, which makes things a little bit easier. And that's because this amount is really negligible when we're considering small angles. And of course we're considering small angles because we're looking at if it's unstable or not, which only depends on the small, which is looking at how it changes with small perturbations. So essentially what we have here is we have to find the center of buoyancy of this new trapezoidal shape after it's rotated. And if the center of buoyancy is on the right side of the center of mass, so let's say the center of buoyancy is somewhere like here, that means the buoyancy force is going to point upwards and it's going to be stable. However, if it is not and it's on this side here, then it's going to be unstable. So we need to find when it's essentially at the center. So we need to find the center of mass of this trapezoidal shape, and we want to see if it's left or right of this axis here. So the neat trick we're going to use here, we can break this shape up into several different pieces. You could do it like this, and this works just as fine. It's almost exactly the same calculations. But we can also do this neat trick here, is where you take this original center of mass and then take the original water level and then say this is the original water level plus negative water, which means it's like 2 times on this side. I don't know if that was a bit confusing, but we say this is a superposition of this rectangle and then this triangle, which has density negative rho W, and this triangle here, which has density rho W. So that's effectively putting a triangle on this side. So the center of mass is going to be a combination of the center of mass of this piece, and that piece. And so let's look at, and let's move over that piece. So it's essentially this piece with double the mass plus that piece. And here, the center of mass is, using geometry, it's going to be 2/3 the way along here. So 2/3 of 1/2 is going to be 1/3 s, if we let the side lengths be s. So it's 1/3 s, and let's say the small angle is theta. Then the mass here, which will count as area because it's uniform density, the mass is 1/2 s squared sine theta, which is approximately theta. That shouldn't end up mattering too much though. So 1/2 s squared sine theta times 2, because this negative part moves over there. And the distance here is 1/3 s. And we're just going to look at the horizontal coordinate because that's all we care about. Of course, that doesn't matter because of the lowest order, the horizontal coordinate and the distance is the same. So we need to add that to, and we need that to be equal to the mass of this rectangle times this deviation here. And the mass of this rectangle is approximately just this, is approximately this rectangle that's underwater from the start. And so that means that this length here, from here to here, it's called x crit, is essentially the same x here. So that over s is equal to the ratio of the density of the log to the density of water. So we need this to be equal to x crit times s times the x coordinate here, and the x coordinate is going to be, so the distance from the center to this point here is going to be s over 2 minus x crit over 2. So times s over 2 minus, I'm just going to say x over 2, and we need this relation to be true. So we can simplify some stuff here, and let's multiply by 6 everywhere, so that gives us 2s squared. Oh yeah, and we also have to multiply by sine theta, of course, and canceling sine theta, so that gives us 2s cubed is equal to, and let's cancel an s here, so it'll make it s squared, is equal to 3x crit 3xs minus 3x squared. So 3x squared minus 3xs plus 2s squared is, you guys see, I realized I just made a mistake here from back here, and this shouldn't be s squared because this triangle has side length s over 2. This should be s over 2 squared, and this isn't going to affect too much. It's just an over 4 here, so it's over 2, and we should multiply by 2 again, and that gives us, you can just do that pretty much in your head, minus 6ss plus s squared is equal to 0. So by quadratic formula, this gives us x is equal to s times 6 plus or minus the square root of 36 minus 24 over 12, which is equal to s times 3 plus or minus root 3 over 6. And the relevant root here is, since we're looking for the critical density, which would be the smallest density, is equal to s times 3 minus root 3 over 6. So the critical density is rho c over rho w is equal to x over s is equal to 3 minus root 3 over 6. And we can just multiply out rho w to get the desired answer. Alright, that was a lot less math than, of course, this one here, but still quite a bit of math, and you need a bit of geometry to complete it, but it's quite an interesting problem because the system is deceivingly complicated. Like, when you first look at it, it seems simple, but after you look at it, it's a lot less simple. Alright, let's look at problem 16. A hemispherical container is placed upside down on a smooth horizontal surface. Through a small hole at the bottom of the container, water is then poured in. Exactly when the container gets full, water starts leaking from between the table and the edge of the container. Find the mass of the container if the water has density rho and the radius of the hemisphere is r. So for this problem, Obviously, what we can do is find the pressure at all of these points along the hemisphere and add up the forces, which get progressively longer as you go down. But here's one neat trick we can use. We can look at the entire force on this water plus hemispherical container and set that equal to 0. So we have the gravitational force from here and the gravitational force on the container, and we also have pressure from the bottom here. And if it's leaking, it means that the container is not actually touching the ground. The only upward force is actually the pressure. So we can set the pressure times the area equal to, obviously there's a pressure from above, but we take the we don't take the actual pressure, but we take the change in pressure, and we take the pressure times the area is equal to mg plus the second gravitational force, which is 4/3 pi r cubed rho g. So from there we're really almost done, and we just can we need to plug in pressure, and then we can solve for mass. So pressure in this case is given by the hydrostatic equation, which gives us pressure is equal to rho gr, and the area is pi r squared, so rho gr times pi r squared minus 4/3 pi r cubed rho g is equal to mg, and sorry, this is not 4/3 because obviously that gives negative mass. This is 2/3 since it's the hemisphere, and that gives us 1/3 pi r cubed rho g is equal to mg. So m is equal to 1/3 pi r cubed rho. And so that's the last problem for today. It was a lot more simpler, and of course you can carry out the standard integral, which is also not very difficult, but this neat trick here makes it pretty nice. I hope you enjoyed the video, and thanks for watching.